All right, we're going to do a question here. Let me pull up the review here. Should have had this prepared prior. I didn't have any changes. So we're going to look at finding area of power or of polar equations. So we'll get through some of these pretty quickly, I suppose. I guess I already have the image here, whatever. So we're going to look at this first one. It wants to represent the entire area of the curve R equals 1 plus cosine theta. So to represent the entire area, it would just be your equation for the full rotation of the axis. So that one's pretty simple, right? The hardest part about these questions for me is figuring out what the bounds are going to be, especially with like overlapping curves or specific angle measurements. So, but when it asks you to integrate the entire thing, it's pretty easy. I think this one looks like this or something. Maybe this way. Yeah. So here's 0, and then it's going to go all the way to 2 pi. I like to imagine this angle here, and at this angle, there's a point plotted right there. At this angle, there's a point plotted right there. At this angle, point plotted right there. So I kind of think of it as like a radar where this thing comes swinging around. Also notice that this bottom bound is where this spinning thing starts. And then this one represents where it's going to end. So that's the full rotation there. Let's look at one petal of the curve R equals 4 cosine 3 theta. So the graph of this equation looks a little something like this, with theta equals 0 at 4. So we want to see when R equals 4 cosine 3 theta. We want to see when R equals 0, and that would just be 4 times cosine 3 theta. So we just need to find out when cosine 3 theta is equal to 0. And it's equal to 0 in a lot of spaces, but we want to find this first one, because we're going to calculate the area of this petal. And we don't want to find like this 0 or this 0 or this 0. I think there's a total of 6 zeros here, right? Because each petal has a beginning and end. So if we calculated like pi over 2, for instance, then the angle fed into here would be 3 pi over 2, and we'd be finding this angle. But that's a little too far. We want to find this angle. We want to find these two. So let's set, we know that cosine of theta is equal to 0 when theta is equal to pi over 2. So let's set 3 theta equal to pi over 2, right? If this is easier, what you can do is substitute this inner part with some variable and then solve the equation like that. And then just replace your variable here. So if we solve for theta here, we will get pi over 6. So we know that this first angle here is going to be pi over 6. And that makes sense because if we plug pi over 6 into here, multiply that by 3, we're going to get pi over 2, and cosine of pi over 2 is equal to 0. So next we want this angle. And this shape here is symmetrical, so we're going to have pi over 6 up here, and then this is just going to be negative pi over 6. And if we use that method that I explained on the last problem, where we have our lower bound as our starting point and our upper bound as our end point, it's clear to see that we're going to start at this angle, at this one, and we're going to sweep over this way. And as we sweep over, this thing comes here. So as negative pi over 6 increases, it increases, it increases, it's growing in r all the way up till it gets to 0. When theta equals 0, that is at the peak, because that's when cosine equals 1. And then as it increases more, it's going to go down, 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 back to 0. So let's set up our integral with our lower bound as negative pi over 6 and our upper bound as positive pi over 6. And then we can just plug in the equation. You get 4 cosine 3 theta squared d theta. And this will be your answer for that next one. Finally, let's look at the third question, which is an integral that represents the area, the outside of the graph of the curve r equals 7. So this will be 7. And the inside of the graph of the curve r equals 7 minus 7 sine. So that is going to be a cardioid that kind of looks like this. And you can see here that these intersect at 7. If you didn't have the graph, what you could do is set these two equations equal to each other, find when they're equal, and you get something like 0 equals sine. And this is true when theta is equal to 0 or pi, or 2 pi. All of those are true. And this makes sense. We have 0 right here, 1 full rotation over, or 1, I guess this is half a rotation over, is pi. So we want to find the area outside of this circular graph, but inside of this cardioid. So what we're solving for here is this little slice of cake. Kind of looks like a guy. So the easiest way that I understood how to do this was neglect everything up here, right? Because all of our area is bounded by this x-axis, and it's right here. So I don't need to worry about what the r values are during the time period between theta equaling 0 and theta equaling pi. What I care about is this section. So I'm going to set up an integral where we start here and we end here. So I'm going to have my lower bound equal to pi and my upper bound equal to 2 pi. So if I'm calculating this, I want to subtract this area from the entirety of this area. And when we do that, we'll be left with just this sliver. So let's do that. I'm going to bring this 1/2 out front, and I'm going to have our r squared of our outer one first, right? I'm getting the whole area first of 7 minus 7 sine theta squared, and then I'm subtracting this area from it. And the difference of those two parts, right, equals just this little half moon. So this is 7 squared d theta. And this will be the answer for that one. Let's look at one example of arc length. I think these ones are much easier. This is very nice and simple, in my opinion. At least compared to the finding the area of these. Holy cow. We have a Hindu reference. Let's set up the equation. Let's remember what the equation of arc length is for a polar equation. It's going to be r squared plus dr over d theta squared d theta. Maybe these are just easier because they give you the bounds. But so our r is equal to 6 sine, which means our dr d theta, just taking the derivative of it, is going to be 6 cosine theta. So our integral is very simple. It's 0 to pi over 2, because these are the bounds that are given, square root of 36 sine squared plus 36 cosine squared d theta. So this looks pretty simple. It'll simplify to, if we take this 36 out, then that'll just simplify down to a 6. Then we have sine squared plus cosine squared, which is 1. Square root of 1 is 1. So that'll be this. Is equal to 6 theta, evaluated from pi over 2 to 0. This whole thing is equal to 3 pi. So those are really nice and easy. So at least we have something, right? This review document that I have only has 3 area problems, and they were the 3 that I just demonstrated. And they seem deceptively simple compared to the homework problems, but hopefully this can give you an idea, a theory, and I don't have a firm understanding of this, so don't take this video as, scripture or whatnot. And if you have any recommendations or clarifications for my explanation, that would be greatly appreciated so that we may all understand these concepts more thoroughly. Thank you very much.